Standing waves. Since we've been talking about waves, we derived the wave equation, we solved the wave equation to get plane waves. We talked about plane waves inside of homogeneous media. Then we introduce an interface, and we saw that we get a reflection and transmission and refraction and Brewster's angle and critical angle. Our next topic is to look at what happens when we have this reflected wave overlapping our transmitted wave. And the interference, or the combination of those two, lead to something called a standing wave. So we'll talk about that. We'll visualize it, a bunch of different waves, and then we'll end this with a discussion of the standing wave ratio, which is a metric that we'll use to quantify standing waves. Standing waves. So let's say we have two waves and they're traveling in opposite directions. So all that's happening here, we have two waves approaching to each other, and all I'm doing here is adding them. And let's watch what happens, and they have equal amplitude. When they start to overlap, we start seeing these huge swings in amplitude. And that's not happening to each of the individual waves, that's happening when they're overlapping. We also see that this swing up and down goes to zero. Another thing we'll notice is that these large fluctuations, those are not moving. And that's actually why we call it a standing wave ratio, because these fluctuations, while they're bouncing up and down, in terms of their left and right movement, they are stationary. They're standing still. So it's a standing wave. Now let's look at a different case. The same thing is happening, except I've made the amplitude of one of those waves obviously much smaller than the other one. And again, I am just adding these. Now watch what happens when they start to cross. We also observe a fluctuating overall amplitude of these. The position of those fluctuations is stationary. It's standing still. However, we notice that those fluctuations aren't going as high, and they're also not going to zero. That's an indication that the two waves are not of equal amplitude. They have to be of equal amplitude to go to zero, because they have to exactly cancel each other. And then, of course, if one of the waves is smaller, their sum, of course, won't be as big as two waves of equal amplitude. So let's set up our problem. And we have this configuration with an incident wave, a transmitted wave, reflected wave, and that's what we've been talking about. And on the left, we have our expressions for all of those waves. For the magnetic field, we're expressing that as the amplitude of the electric field divided by the impedance. We're doing the same thing for the reflected wave. And remember, there's a negative sign here because of the handedness. We don't need any expression in this case for the transmitted wave, because the standing wave is completely on the left side of the interface where we only have the incident and reflected wave. So for this analysis, we don't really care about the transmitted wave. Now let's look at the materials for a reflection, and we'd like to simplify this down so it's not too complicated. So let's look at the case when we have some kind of lossless dielectric on the left and we have a metal on the right. So the conductivity is super high. So on the left, when we have a lossless dielectric, we just have the impedance, which is the square root of the ratio of permeability to permittivity, as usual. But for the metal, the impedance goes to zero, and that's a perfect metal. And it turns out this will simplify our math. So when that impedance is zero, we set eta 2 equal to 0 in both of these equations for reflection and transmission. And what we see is we get a -1 for the reflection coefficient and 0 for the transmission coefficient. We have a perfect metal there. It completely reflects it, so it doesn't transmit at all. It completely reflects, the magnitude is 1, and the negative sign indicates that when a wave reflects off of metal from a dielectric, it experiences a 180-degree phase shift. And we'll see the consequence of this later on in some simulations. In terms of our other parameters, we have a complex propagation constant in medium 1, which is an alpha plus j beta. And we can plug in our values to get alpha and beta where the conductivity is 0. And what we end up with in medium 1, since it's lossless, we have 0 attenuation. And our beta term, our phase constant, is omega times the square root of mu epsilon. And from previous discussions, this should not be a surprise. So given all these different parameters, we can plug them back into those wave expressions for the incident and reflected wave. So our expressions for the incident wave, what has changed here, since it's lossless, there's no alpha in that complex propagation constant. So we just replaced it with a j beta. We only have the phase constant. And in fact, all of our complex exponentials now have beta in it instead of our complex gamma term. The incident wave, the amplitude terms stay the same. Now the reflected waves, we now know that the amplitude of the reflected wave is the amplitude of the incident wave times our reflection coefficient, which, by the way, we also know is -1 for this case. And also for the magnetic field component, we have the amplitude of the reflected wave, which is R, our reflection coefficient, times the amplitude of the incident wave, divided by impedance, and the negative sign is still here because of the handedness change. And our complex exponentials have a positive sign here because we're talking about a backward wave. So the reason we're doing all this, we're minimizing the number of different parameters. Everything now has this amplitude, the electric field amplitude of our incident wave. So we're eliminating variables to simplify things down. We're going to look at the equations for standing waves, first in the frequency domain and then in the time domain. So we're looking at the total field in medium 1. So the total field we write as E1 and H1, which we know is the incident wave plus the reflected wave for both electric and magnetic fields. Well, we also have our expressions now for the incident and reflected fields for both electric and magnetic components of that. So we can write those in. Now remember, there was an R sitting here. However, also remember the R was -1. This was a positive sign. It was a plus R times the E naught for the incident wave. And so we replaced that positive R with a -1. And then we have our magnetic fields as well. Now, in the first equation, we have two complex exponentials, but otherwise we have some common terms. We have this amplitude of the incident wave on both terms, and we have the x direction in both terms. Likewise, down here, we have this ratio and this ratio appearing twice, and we have our unit vector in the y direction. So we can factor these out, and we're just left with these complex exponentials. And if we look at them long enough, what we see is that these are actually our sine and cosine functions. So we can replace those with sines and cosines. When we do that, we end up with these two expressions for the total field in medium 1. Now let's derive our expressions for the standing waves in the time domain. So our total field, E1, is now a function of z and time. And of course, our magnetic field we'll be doing the same thing with. So we start off with our expression in the frequency domain, and we convert it to the time domain just by getting the real part of that. So the first thing we'll do is factor out a bunch of terms from the real operation. So everything complex is left inside the square brackets. Then we can convert the e to the j omega t into sines and cosines using Euler's identity, and then just take the real part of that, and we end up with our expressions in the time domain. And both of them have a similar form. There's an amplitude. Notice it's twice the amplitude. That's because we've assumed both of our waves have the same amplitude, so they can add together to be twice the amplitude. We have the sine beta z. Beta is a constant, so this is not an oscillating term. This is defining an overall envelope of the standing wave. Then we have a sine omega t. This is oscillating. This is oscillating with the frequency of our wave, but it's oscillating within the envelope of this sine. So we'll understand that this sine is actually the more important term here because that's what's defining our standing wave. We see the same thing for the magnetic field. We see this 2 out here because we have two waves adding together. Our standing wave is now a cosine term instead of a sine term. So we can expect our standing waves for the electric and magnetic fields to be shifted a quarter wavelength apart. And we have this other cosine term, which is the oscillating field, which won't play much of a role in our standing wave, other than we're watching in the time domain and we can watch the wave bounce up and down. But the envelope of the standing wave will be defined by this cosine. Now we did that whole example for when R is -1, when we're going from a lossless dielectric to a metal and we get 100% reflection with a 180-degree phase shift. If we had assumed that R was +1, so there is no phase shift, these expressions is what we would get for our frequency domain equations, and then these expressions down here is what we get for the time domain equations. The basic form of them is the same. We have an envelope term and an oscillating term. It's just that the sines and cosines have moved around and switched equations, if you will. Now let's start looking at these standing waves and see what's going on. So there's a lot on this slide, so let's take this slowly. This is for the case where the reflection coefficient is -1. That happens when the impedance of medium 1 is greater than the impedance in medium 2. For this case, here are our two expressions for the electric and magnetic field. And down here is a simulation and a visualization of what is happening. So I'll direct your attention first to the incident electric field. So this blue ribbon is visualizing our incident wave. Now that hits this interface between impedance 1 and impedance 2, and we made this a perfect metal, so that reflects. And here we're visualizing the reflected wave in this second blue ribbon. Now if I add these incident and reflected waves together, I get the third ribbon here. So this third ribbon is visualizing our standing wave. And we see that the fluctuations, while they're bouncing up and down, those fluctuations are not moving left and right. Thus, it is a standing wave. Another thing I'm doing is I'm marking every quarter wavelength with these vertical lines, because what we're going to do is compare it to the standing wave for the magnetic field component next. So down for the magnetic field, we have the same things. Here's the magnetic field component of the incident wave. Here's the magnetic field component for the reflected wave. And if I add these two ribbons together, I get the ribbon for the standing wave for the magnetic field component. So from red line to red line, that's marking a half wavelength. And from blue line to blue line, that's another half wavelength. But from blue to red, these are our quarter wavelength steps. And these lines help us compare what's happening to the two different standing waves. First, notice the total field, or our standing wave, right at the interface stays at 0. Well, this is a perfect metal where the electric field is 0. So the total field just on the other side must also be 0 in order to satisfy the boundary conditions. That is why the reflected wave has a 180-degree phase shift, so it can add to the incident wave to completely cancel at the interface. Now from there, our standing wave fluctuates. And what we can see is that a quarter wavelength away, here's where we get our maximum fluctuation in the standing wave. If we back up another quarter wavelength, here the standing wave isn't doing anything. It's staying at 0. And this keeps repeating. We back up another quarter wave, we see these huge fluctuations. So the points where the standing wave is not fluctuating at all, those are sometimes called nodes. And where it's fluctuating the most, those are sometimes called antinodes. Now let's compare the fluctuations from the magnetic field to the electric field. Right at the interface, the electric field is not oscillating at all. The standing wave for the electric field is not oscillating at all. But if we look at the magnetic field, we see that the same point is actually the point of maximum fluctuation. If we back up a quarter wavelength, at this point we're at a magnetic field node, so the standing wave is staying perfectly stationary. And if we come up and look at the electric field, this is where it has its maximum swing. So the nodes and antinodes for the electric and magnetic fields are opposite. Where the electric field has its minima, the magnetic field would have its maxima. And the other way around, where the electric field has a minimum, the H field will have its maximum. So I think we've observed about everything. I'll repeat the important things. The one important thing is that this repeats. Every half wavelength, the standing wave repeats. We would maybe expect just at a cursory glance at every wavelength it would repeat, but that's not true. Every half wavelength, our standing wave repeats. Every quarter wavelength, we go from a minimum swing to a maximum swing. And the electric and magnetic field components of that standing wave are shifted from each other by a quarter wavelength. Maxima of one corresponds to minima of the other. Now this is the next case where we had our reflection coefficient being positive 1. Almost all of the same conclusions can be made here. Let me point out some important differences. But we're still looking at the applied electric field, the reflected electric field, and then we're adding both for the electric fields. Notice now, at the interface, the electric field has its maximum swing. That's due to the reflection coefficient being a positive 1 instead of a negative 1. When it was negative 1, it was 0 at the interface. And you can rewind the video and look at that. Now in this case, when the reflection coefficient is positive 1, now the magnetic field is fixed to 0 at the interface. But from this point forward, it's the same story we had before. If we back up a quarter wavelength from an antinode, we get to a node. When we compare the electric field standing wave to the magnetic field standing wave, they are shifted by a quarter wavelength. So the maxima of E is still a minima of H, and a minima of E is a maximum of H. And so we also see that the standing wave pattern is a quarter wave shifted from what we had on the previous slide when our reflection coefficient was negative 1. So this is a little bit more rigorous and meaningful visualization, and maybe it's not as cool as looking at something that's more three-dimensional, but this is the case where the reflection coefficient is negative 1, and we're looking at this from the side view now. And so the electric field is definitely 0 at the interface. This dashed blue line is showing the envelope of the standing wave. And so we can see that that is not moving. This thick blue line, being our standing wave, isn't moving. It's fluctuating up and down, but not moving left and right. Our applied wave is shown by this green line. And then, of course, the reflected wave is shown by the gray line. If we add them together, we get the blue line, and the blue line is the standing wave, and it oscillates within this envelope. So this envelope, by the way, is our cosine function. That's the envelope of our standing wave. Now if we go down to the magnetic field, I'm showing the magnetic field of the incident wave in green, and then the gray is showing the magnetic field component of the reflected wave. If I add the green and the gray, I get this thick red line. That's the standing wave for the magnetic field, and it is oscillating in the envelope of this red dashed line, and the red dashed line being this sine beta z term. And we can see at the interface, the magnetic field has its maximum swing. The electric field has its minimum swing. We back up a quarter wavelength. Now the electric field has its maximum swing. The magnetic field has its minimum swing. In this case, it's 0. Same visualization now, but for the reflection coefficient being positive 1. It's really the same picture. The difference is our standing waves have slid either left or right by a quarter wavelength. So our electric field at the interface, instead of being a 0, is its maximum. Now the magnetic field at the interface is 0. But we keep backing up every quarter wavelength. Nodes become antinodes, then nodes again, then antinodes. And the electric and magnetic fields are still shifted from each other by a quarter wavelength. And every half wavelength, the standing wave pattern repeats. Now let's get quantitative about the severity, if you will, of our standing wave. And we'll use the standing wave ratio to do that. The standing wave ratio is a very easy metric to measure, whereas reflection is a bit more difficult to directly measure reflection. So instead, we don't actually have to directly measure reflection. We can measure the standing wave ratio and then really infer what that reflection was. Let's see how this works. So here is a visualization how we've been doing, but it's a bit more generalized, where the applied and reflected wave are different amplitudes, and that happens because I'm not making this medium here a perfect conductor. So we just have two impedances, so there's a somewhat small reflection, and our reflected wave is smaller than the applied wave. Since they're not of equal amplitude, that means our standing wave will not go down to zero. It has a minimum and a maximum. And it's based on this minimum and maximum that we quantify our standing wave ratio. So we will define it as the maximum electric field that we observe divided by the minimum electric field that we observe. And by the way, we could define it the same way with magnetic fields and we'd get the same answer. So we just define it in terms of the electric field and we're pretty happy. In this case, our reflection coefficient is 0.33. And that's how we're getting the smaller reflected wave compared to the incident wave. Let's derive an expression. So the total electric field, of course, is the incident plus the reflected, and we derived this expression. And we derived this expression really before we used Euler's identity. The difference is now we're leaving this reflection coefficient in here because it's not just plus or minus 1, which let us convert those exponentials to sines and cosines. We're leaving the r in there. Now we have to think what is, based on this equation, what is the maximum value we can get for E1 and what's the minimum value? Well, these complex exponentials are essentially trig functions. They're confined between -1 and 1. They can't be larger than that. So the biggest number that we can get in here is when this complex exponential is 1 and this is 1, and we just look at the magnitude of r. So it's really 1 plus r. That is the maximum that we could possibly get. The minimum that we could get is when this exponential is 1 and the other one's -1. So the r is subtracting as much as it can from the positive 1. So we have a 1 minus magnitude of r for the minimum value of E. Now that we have those expressions, we can plug those back in our definition for standing wave ratio. So the standing wave ratio is defined as the maximum value of the electric field divided by the minimum value. We now have expressions for that, and of course these two amplitude terms will cancel because they're the same. And we end up with our final equation for the definition of the standing wave ratio in terms of our reflection coefficient. So it already makes a little bit of sense. If we know the standing wave ratio, we could probably back calculate at least the magnitude of our reflection coefficient. Let's derive this in terms of the magnetic field. So we have our total magnetic field, which is the incident plus the reflected. We had this expression. Difference is we're leaving r as r now. We're not making it a positive or a -1. We need to get from this the maximum and minimum values of the magnetic field, and the same rules apply. So a maximum happens when we have a 1 plus r inside these parentheses, and a minimum happens when we have a 1 minus magnitude of r. So we can throw those into our definition of standing wave ratio, and what we can see is we get the exact same equation. So if for some reason the magnetic fields happen to be the easier thing to measure, that's fine. Measure the magnetic fields and calculate the standing wave ratio. If you have more immediate access or easier measurement of electric fields, use that. You'll get the same number for standing wave ratio. Now, very often we express the standing wave ratio in dBs. That's because there's a huge variation in values that we can get for our standing wave ratio, and it can span many orders of magnitude. And so when this happens, it's usually more convenient to express this on a dB scale. So if we're given just the standard linear standing wave ratio, it's 20 times log base 10 of SWR. Why the 20? Because the standing wave ratio is derived from amplitude quantities, but dB is always power, And so we need to square those amplitude quantities. And so we get a 20 here instead of a 10 because that squared comes out here. Decibels defined as 10 log 10, but if we put amplitude quantities in here, that squared comes out, making it a 20. Now we can do this the other way around. If we're given the log SWR, the SWR in dB, we can then calculate the linear SWR from that. We just divide our dB standing wave ratio by 20 and then use that as an exponent on 10. So we can convert back and forth. So here's one useful thing. We can start with our definition of SWR, and here's our definition, and we can go through a series of algebraic steps and we can solve this for the reflection coefficient. Now we have a way of something that we can measure easily, standing wave ratio, to sort of indirectly measure something that will be much more difficult to measure otherwise, and that is the reflection coefficient. Let's end our discussion with some final notes about the standing wave ratio. Remember that the magnitude of our reflection coefficient is bound between 0 and 1. So if we put these limits into our equation for the standing wave ratio, what we see is that the standing wave ratio is bound between 1 and infinity. We can't have a standing wave ratio less than 1. And we can't have a standing wave ratio greater than infinity, obviously. So there's really no upper limit for standing wave ratio, but there's definitely a lower limit. It does not make sense to have a value less than 1. When that standing wave ratio is very large, that means our reflection is very strong. When the standing wave ratio is infinity, that does not mean our reflected wave is infinity. That means our reflected wave is 100% of the incident wave. We have a 100% reflection, so it's of equal amplitude to the applied wave. Being equal amplitude, that means it can cancel and go all the way to 0. And so when we divide by 0, that's actually how we get the infinity in the standing wave ratio. So standing wave ratio of infinity means a 100% reflection, so that the reflected wave is the same amplitude of the applied wave. It can cancel all the way to 0, giving us the infinity. So a standing wave ratio of 1, and by the way, when we express that in dB, that's 0. That means we don't have a standing wave at all. The reflection must be 0, or something else has somehow eliminated our backward wave. When the standing wave ratio is infinity, we just went through this, the standing wave ratio in dB is also infinity. And it's a very common mistake to think that means an infinite reflected wave, and that's not true. It just means the reflected wave and the applied wave have the same amplitude so that they can cancel and go all the way to 0. So an infinite standing wave ratio means the reflection coefficient is 1. We're getting 100% reflection. Let's end our discussion of standing waves with a simple example. Let's say we have a wave propagating inside of a medium with 50 ohms, and it encounters an interface with a second medium, and the second medium has an impedance of 120 ohms. We could ask some questions here. One, what fraction of power is reflected? And then what is the standing wave ratio due to that reflected wave? Actually, it's due to the interference between the applied and the reflected wave. So the first thing we can do is calculate our reflection coefficient. And we derived this several lectures ago, and fundamentally it's a change in impedance that causes reflections. So we throw in our impedance values and we get a reflection coefficient of 0.4118. Don't mistake this for a 41% reflection. Once we talk about percentage, we're really implying power, and this is little r. That is an amplitude term. So to determine the fraction of power reflected, that's the reflectance. It's the magnitude of the reflection coefficient squared. So we square the 0.4188 and we get 0.1696. That is about 17%. So we get a 17% power reflection at that interface. So now we have this backward wave that's considerably smaller than the applied wave, but definitely not insignificant. What is the standing wave ratio? Well, we apply our definition of standing wave ratio, We plug in our numbers for that reflection coefficient, not the reflectance here. It's the reflection coefficient that we use in the standing wave ratio equation. And we work our math, and we get a standing wave ratio of 2.4. Now we'd like to express that in dB. So it's 20 log base 10 of our linear standing wave ratio, and we plug in the numbers. We end up with 7.6 dB. And dB is the most common way that standing wave ratio is expressed. So I hope this lecture was helpful to you.